Okay, so here we're going to take a look at bounded sequences. So what that means and how that'll help us to determine whether a sequence is convergent or divergent. All right, so we have two different ways that we can bound a sequence. One is from above, right? So bounded above, it means that for a sub n, there's some real number where a sub n is less than or equal to n for all positive integers n, right? And what this means, right, if you think of this graphically here, is that if we talk about this idea of bounded above, that there exists some value m where all of my a sub n's, right? A sub 1, a sub 2, right? A sub 3, a sub 4, right? Whatever behavior that exhibit. But there does exist this upper bound, right? Where below this, all of my sequence lives, right? And then the same goes for bounded below, right? Bounded below says that a sequence a sub n is bounded below if there exists a real number n such that m is less than or equal to a sub n, all right, for all positive integers n, right? And now here, all right, so in this case, all right, so we think here, right, m, then kind of does this, right? So it's bounded below by that value n, right? So all of the sequence terms lie above or possibly equal to n. Now, in terms of convergence, we say that a sequence is a bounded sequence if it is bounded above and bounded below. If a sequence is not bounded, then it is an unbounded sequence. Right now, an example of an unbounded sequence, we can think of, let's say, just basic 1n squared. All right, and if we kind of graph these, 1, 2, 3, 4. Right, at 1, that's 1. Right, at 2, essentially just the discrete, the integer, positive integer points of a parabola, right? 4. Right, then at 9, then it goes up here, right? While we can bound it below by 1, right? There's no value that I can think of that is bigger than all of the squared values, right? Because what is happening here is any n that I choose, right? Then I can choose the next one, and that one will be bigger, right? It'll be a bigger square, right? So this is an example of an unbounded sequence, all right? It needs to have both of the qualities bounded by below and above in order to be called a bounded sequence. Now, in terms of convergence, here it says convergent sequences are bounded. All right, so if a sequence a sub n converges, then it is bounded. Now let me write this down because I want to be careful how we interpret this, right? So here, if a sequence a sub n is convergent, then it is bounded. It is bounded. All right. Now I do want to be careful how we interpret this theorem as it stands, right? So let me double check here. Converges, then it is bounded. All right, so this theorem applies to convergent sequences, right? So if I know that, if I've shown that it converges, then I have shown that it is in fact a bounded sequence. All right, now be careful how you read this, right? So these if-then statements, right? If you're ever taking a logic class, or if you are currently taking Math 8 or plan to, then this will come up a lot, do some computer programming. The logic of these if-then statements is very important, right? So we have if, we'll call this as our hypothesis, right? If P, or actually let's just use straight symbolic notation. This is the hypothesis, so what we assume to be true. So I have to have under the assumption that P is convergent, then P implies Q, right? Then it is bounded. Now, be careful because a sequence can be bounded, but not convergent, right? So the converse, Q implies P, this is not true, right? A counterexample would be this idea -1 to the n, right? Where we think of this going from, right, -1, 1, -1, 1, -1. All right, so here, excuse me. So in this case, we do have, it is bounded below and above, but above by 1, below by -1, but it is not convergent, right? As n goes to infinity, we oscillate between 1 and -1. So in order for it to converge, the limit has to exist, right? And the limit can only converge to one value. And that does not happen here, okay? So just keep in mind that when we have P implies Q, Q implies P, which is called the converse, that we're not guaranteed for that to be true. Sometimes it could be, right? And that lends to a different type of statement where we have an if and only if, right? It's stronger than an if then, right? It's equality when that happens. But what we can take from this, right, if we're dealing with determining whether I found the bound for a sequence or not, right, what is always true, right? If P implies Q, right, if I know that this is true, then what is always true is not Q implies not P. Now that is helpful, right? Because now if I show, so what this is telling me that if a sequence is unbounded, all right, that would not Q be, right? If a sequence is unbounded, then it is not convergent. And that is helpful here, right? So I can approach problems with this idea of bounding it and not bounding it, all right? And if it's not bounded, then it is not going to be convergent, okay? But just be careful. Again, these if-then statements, they're tricky. They always kind of throw students off. But just make sure that that if-then statement, when you reverse that around, we're not always guaranteed a statement, right? The converse is not always true. But this, what's called the contrapositive, that actually will always be true if we've established that P implies Q. Okay, so now there's a specific type of bounded sequence that we have here. And these are this idea where a sequence is increasing or decreasing, right? So it's decreasing if the next term is always less than or equal to than the previous term. It's increasing if the next term is always bigger than or equal to the previous term. All right. If this is the case, we have what's called a monotone sequence. Now, if we put this together, the monotone sequence with our bounded sequence, then we can establish convergence, right? We say if a sub n is bounded sequence and there exists a positive integer n naught such that a sub n is monotone. So it doesn't have to be across all n, but after a certain value of n, then this is true, then a sub n converges, right? Now graphically, what this is telling me here, right? Let's say, so it's bounded and it's monotone. Now, monotone doesn't have to occur across the whole domain here, right? So maybe it starts off here, then it does something like this, but then after it goes up here, but then maybe after that, it starts to be monotone. It's strictly decreasing, right? But it's monotone and bounded, right? So that means that it's getting, after this point, right, whatever that is, then it's a strictly decreasing decreasing sequence, but it's also bounded, which means that it's bounded by this value m of the values that it can attain, right? So if both of those conditions hold, where it's monotone and bounded, then we can assume convergence, right? And that's what this is telling us here, right? So if I know that it's monotone and bounded, right? Both of those have to be together, right? Because it can't just be monotone, right? Because the previous one that we looked at here, this x squared one, that one is monotone, right? It's strictly increasing as n gets bigger and bigger, right? It's increasing, not convergent, right? So monotone along with boundedness, that is going to give us convergence. Okay, so monotone after a certain value, monotone plus bounded, then that is going to give us convergence. So just keep that in mind, right? That's how we determine here, right? And that's what this theorem is telling me. Okay, so let's take a look at a couple of examples here that we'll be working with factorials, right? Now, these are always tricky in the sense that they do involve, working with factorials, which we really can't apply our stuff from functions, right? When we talk about functions, we are looking at continuous functions, or really functions just defined across real numbers. And the factorial is not, right? As we've seen in a previous video, the factorial is strictly defined off of whole numbers, right? So those techniques of like L'Hopital's and just our general function techniques do not really work here, right? So for this example, right, I like to determine if n factorial over 2 to the n converges or diverges. Okay, so the general term of a sub n is going to be n factorial over 2 to the n, which is equal to 1/2 times 2 times 3 times 4, etc., till we get n minus 1 over n over 2. And then down here, it's always just factors of 2. All right, and then just kind of, let's write out the first couple terms, right? These are always require some kind of analysis here to kind of determine how I'm going to approach this. So it's always helpful, for me at least, to write out the first few terms here, right? So A1 would look like this. A2 looks like this, right? 2 factorial over 2 squared. Here we get 2 times 1, or 1 times 2, however you want to write it, over 2 times 2. And actually, I think I want to establish a pattern here, so I'm going to write it like this. All right, so this is also 1/2, right? These 2's are going to simplify to 1, so we're left with 1/2. All right, it doesn't tell me much just yet. If I keep going here, A3, now we got 3 factorial over 2 to the third. So 1 times 2 times 3. Okay, and then here again, as before, right, those middle 2's, right, or the 2's, those are always going to simplify out to 1. So here we're left with 3/4. Okay, now it looks like maybe it's getting bigger, and I don't have enough just yet to establish that fact. All right, so now let me go here, a to the 4th. That becomes 4 factorial over 2 to the 4th. And here we got 1, 2, 3, 4. And then 2 times 2 times 2 times 2. All right, and again, that middle term reduces to 1, and here we'll have 12 over 8, which reduces to 3/2. Now it looks like this is getting bigger, right? Now, how am I going to essentially prove that this is in fact just growing without bound? Well, one thing that I notice here, right? Now it's not always getting bigger, right? At some point we see for A1 and A2, then this just, it gets the same value, right? So I want to establish that it's increasing. So I'm going to actually just kind of start here and establish a pattern here. All right, now the pattern here is, notice here that I'm always going to have a factor of 1, a 1/2, excuse me, right? So that's always going to show up, right? All right, and at the end here, I notice that the last terms here are the n, whatever n is, in this case 3, in this case 4, divided by 2. Right, now this value, when I strictly look at n bigger than or equal to 2, right, that value is always going to be bigger than 1, right? And actually here I should make in this statement here, and oops, strictly bigger than 2, bigger than or equal to. I think that's fine. That should work fine. Okay, so the reason I'm saying this is I'm going to have this factor of 1/2, and then whatever else is happening in the middle here, right, this last term that I'm going to multiply is always going to be bigger than 1, right? So it's going to make it bigger. Whatever this middle terms are going to be, if I account for the 1/2, the multiplication by the last term is always going to be a value that is bigger than 1. So all that to say is that here, I'm going to establish, going back to my initial general term, that this term here will always be bigger than or equal to that 1/2, right? But also times the value of n over 2, because this value is always bigger than 1. Okay, so whatever these terms happen to be here, right, I'm multiplying by a value that's bigger than 1, right? So this part right here will always be bigger than this quantity, right? Now, why do I focus on that? Well, because if I look at this I can actually find the limit for this, right? So let me scroll down here. So we have the limit as n goes to infinity of n over 4, right? And that's what 1/2 times n over 2 is. Well, n just shows up here, so this kind of grows without bound. So this is going towards infinity, right? This one is divergent, right? Well, what does that tell me about the sequence that I'm trying to evaluate? All right, let's go back to our inequalities. Oops. Here, so a sub n, I've established is bigger than or equal to this. So I've established that a sub n is bigger than or equal to infinity, right? In other words, it's unbounded, right? There's no value of m that I could find where it's the biggest value, right? And now what we said here, if I know it's unbounded, then there's no way it can be convergent. If it's unbounded, that means that the sequence a sub n is divergent. Okay, so that's how we approach something like this, where we have a factorial. Now let's take a look at one more example here. Oops. So for this example, I want to determine if -3 to the n over n factorial converges or diverges. Okay. Now, in this particular case, this is an alternating sequence. All right, and I'm going to take a look to set up. I'm going to use the squeeze theorem here. All right. Now, in order for me to do that, I'm going to only focus on the absolute value of a sub n, which will always be greater than or equal to 0. Now, I'm going to use that fact here, and I'll get back to how that helps me actually solve the excuse me, this alternating sequence. So what I have here is here. So when it's the absolute value, so the absolute value of a sub n, it's going to be, essentially, I'm just ignoring the negative for now. So I'm going to be focused on this sequence here, right? And I know that this sequence here, it's bounded below by 0, and I want to find a way to bound it above. Okay, so let's start with the general term here, right? The general term a sub n is 3 to the n over n factorial, right? So that looks like this, right? 3 times 3 times 3 times 3, and then dot, 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 3. And then in the denominator, we have 1, 2, 3, 4 to n minus 1, and then another 3 gives me n. All right. All right, now, as always, I want to just kind of write these out to kind of get an idea of what this sequence is doing. So a1 is 3 over 1 factorial, right? And this equals to just 3, right? And then a2, that equals to 3 squared over 2 factorial. So that's 3 times 3 over 1 times 2. So that gives me 9 halves, right? Which is 4.5, right? So at first I'm like, oh, maybe this is an increasing function. All right, so let's keep going here, right? a3 is equal to 3 cubed over 3 factorial. And here that's 3 times 3 times 3 over 1 times 2 times 3, right? And we see now here these are reduced to 1. So we get a similar type of behavior where in this case, the previous one at 2, in this one at 3, we get a reduction of a factor of 3 in the numerator and the denominator. So we get 9 halves, which again is 4.5. Again, not telling me much just yet. So let's take a look at a4. Right, a4 is 3 to the 4th over 4 factorial, and that looks like this. And then again, we get that same behavior, right? At that point, that reduces to 1, and we get, in this case, 27 over 8. And here we get 3.375. All right, I do that just to kind of establish, now what we're going to see is actually, this is not an increasing function, right? After a2, right, so starting at a3, it's going to reduce, it's going to decrease, right? a5, 3 to the 5th, over 5 factorial. And here we get 3 times 3 times 3 times 3 times 3 over 1 times 2 times 3 times 4 times 5, right? And again, we get the same, that middle one goes to 1, right? Multiplying this out, we get 81 over 40. And this is 2.025. Okay, so now here, a6, one more here, and then I think we will have enough to kind of establish our inequality. So this is 1, 2, 3, 4, 5, 6. All right, and 1 times 2 times 3 times 4 times 5 times 6. All right, and here we get that, a reduction of 1, multiplying all this out and reducing, we get 81 over 80, and that is 1.0125. All right, so now it is decreasing. All right, and we notice here that this factor kind of reduces here. So what is happening here, right, as before, I'm going to take these first couple of terms here, right? Those will always be there, right? So it's always going to be less than these terms here. But then what happens here, right? Notice that the numerator is always going to be 3, right? But the denominator is n, right? Now in this case, in each case, right, once n is bigger than or equal to 3, right, that value there is always going to be bigger than 3, right? Bigger than or equal to 3, right? Well, that means that in the previous one, we're multiplying by 1, but if the top is fixed at 3 and the bottom number is getting bigger than 3, I'm no longer multiplying by a number bigger than 1. I'm multiplying by a number that is less than 1. So what that does is I'm going to take the same approach here where I can bound this in this way. This is going to be less than or equal to these first two terms, right, to account for n bigger than or equal to 3. it's always going to be less than that and this last term. All right, 3 over n. All right, because whatever happens here, all right, when I multiply this, that value is definitely going to be less than this since it is less than 1. Okay? All right, so now we've established that here. And so we want to take the limit as n goes to infinity here of this quantity here. All right, what was it up here? 27. 3 over n, 3 times 9. 27 over 2n. Now here the n shows up in the denominator. So the n is getting really, really, really large. Right? The bottom one is, the top is fixed, constant. So this is all going to 0. All right, so now what I've established here is that the limit as n goes to infinity of 3 to the n over n factorial. Right, the limit's below by 0 because it's always positive, and then above, right, by the inequality that I fixed, so that I take the limit of that, that's going to 0. So by the squeeze theorem, the limit as n goes to infinity of 3 to the n over n factorial is also going to 0. Now, how does that help me do the original one? As it turns out, since the absolute value is going to 0, this one will also be going to 0, right? So if the limit as n goes to infinity of a sub n goes to 0, then the limit as n goes to infinity of a sub n is also 0, right? And that makes sense here because in the first case, if it's going to 0, that means that eventually it converges like that, right? And if we allow for negative values, well, they still, in both cases, right, these negative values that are above will now be below the x-axis, but they're all very near, right? They're all very near 0. So really in both cases, whether it's going strictly positive or we allow for negative values, it will also converge to the value 0, right? This type of relationship only works for 0, because if it's any non-zero number, then as we could see, it'll bounce from values above the x-axis to below, so we can't guarantee that being true, right? But for this instance, we can show here that the limit is in fact 0 for this sequence.